I want to start by thanking the organizers for inviting me to such an interesting and diverse workshop. I also want to thank everybody in the audience for coming back inside on a beautiful Friday summer afternoon. You guys are the real heroes. Okay, so I'm going to be talking about learning from noisy and incomplete data. My background is largely, really entirely in theoretical computer science, computational learning theory, and computational complexity. So what I'll be telling you will be sort of informed from that perspective, which is where I'm coming from. Let me start with kind of a cartoon scenario, which is a very crude generalization of the kinds of frameworks we'll be thinking about. So you can consider a setting in which you have access to some labeled data points. So you can think of the X part as like the example, the data, and the Y part as like the label. And for this whole talk, we'll be dealing with classification rules, binary classification, so the Y's are always bits. Yeses and O's, zeros and ones. You could imagine that maybe the X's, the jth X data point is the description of weather conditions on some morning gathered from some sensors or something. And maybe the Y part is just a bit indicating whether or not it ends up raining that day. Or I don't know, the X could be something like a description and encoding of some kind of molecule you've cooked up in the lab, and the Y tells us whether or not it has a property that you're interested in. Okay? So this is a very general framework. We can imagine all kinds of problems fitting into this. And if we're thinking about prediction, for us, that'll mean essentially the following. If I give you a new data point, so a t plus first X example, you'd like to be able to correctly predict the label that goes along with this point. Okay? And we'll be looking at these problems from really a very sort of theoretical computer science, algorithms, and computational complexity perspective. We'll be trying to think about the running time of algorithms that can solve sort of well-specified problems of this sort. Okay? So I should mention, going back maybe to the well, I'll go ahead instead of going back. I'll be talking mostly about a very clean, I think, and elegant theoretical model of learning, solving learning problems of this sort. That's the so-called PAC learning, or probably approximately correct learning model. I'm going to give you really a survey talk, so I won't brutalize you with anything extremely technical or detailed this afternoon. Instead, I'll just sort of tell you about the state of the art and some upper bounds, so efficient algorithms for solving learning problems in this framework, and some lower bounds, hardness results, or results which indicate that we shouldn't expect to have efficient algorithms for other problems. Of course, we're going to be concerned with, like I promised in the title, learning with noise and learning from partial information. So the original PAC learning model doesn't have these qualities. It really is sort of a very idealized way of thinking about learning problems. But there have been extensions of the model, and people now, kind of intensively study these questions of how can we deal with noise, how can we deal with scenarios where we don't have all the information we would want to have, and so on. So if I get time at the end, I hope to touch a little bit also on some unsupervised learning problems. So I haven't used the phrase yet, but the sort of framework I've been talking about, where you have X and f of X, you have a label associated with each example, is of course supervised learning. I'll also hopefully get to talk a little bit about unsupervised learning problems. And the framework here will be a framework of learning probability distributions, or you could think of it as density estimation as a phrase that's sometimes used in statistics. And there's been some recent work here as well on trying to handle noise, trying to handle partial information for learning problems of this sort. Okay? So kind of a roadmap of where we'll be going. Okay, before I get into details and really tell you what the model is, let me give you kind of a little bit of high-level setup or motivation or intuition. As I said earlier, we'll be thinking of a setting where we get these examples, X, and then we have a label for the example, which is Y. The examples we'll think of as really just a vector of feature values. So I'll sometimes use this term, a feature, to mean one of the coordinates of the example X. We'll always think of X as being a vector, typically a real vector or a Boolean vector if we have categorical data. So maybe an example corresponds to a patient in a database, and we have different coordinates of the vector describing that patient, the height, the weight, so on and so forth. And the label would be something like whether or not this patient responded well maybe to a particular treatment. So the algorithmic kind of problem, the general template for the problems we'll be thinking about, is that we have a data set of labeled examples. So we have a bunch of data points like this, the example and the label. And we'd like to come up with a hypothesis, a binary classification rule, which will do a good job of assigning the correct label to future unlabeled examples that we might receive. And we'll make this framework more precise in a minute. To touch briefly, though, on the properties of the idealized scenario, this original so-called probably approximately correct learning model, which will eventually extend, in the idealized original model, we make some assumptions. The first of these is sort of central to this complexity theoretic or theoretical computer science view on the problem, which is that we're going to really be thinking about function classes as sort of defining our learning problems, right? We'll be in sort of a very well-specified setup where there's always going to be some unknown rule that correctly labels the examples that we have to deal with. I'll talk much more about this later. In the basic scenario as well, we're going to assume we don't have missing data. So I actually know what all the coordinates are for every data point I'm dealing with. And in the idealized scenario, we won't have noise. But again, we'll relax these assumptions as we go further through the talk. Okay? And here's just sort of a crude example of maybe the true unknown rule that we're trying to learn is defined by a linear separator like this dashed gray line. And the learning algorithm, if it's supposed to come up with a high accuracy hypothesis, maybe successfully comes up with something like this black line, right, which is fairly close in some sense to the unknown true classification rule. Okay, so as I said, we're going to be sort of thinking of learning problems as corresponding to classes of functions, classes of classification rules. Okay, so let me be a little bit more precise about this. For us, a learning problem will be defined by a class, this boldface C, of Boolean valued functions over some domain X. So this bold X, that's where the examples come from. It's maybe bit strings of length n, or vectors of n real numbers, something like that. That's what an unlabeled example looks like for us, an element of this set. Okay? What we'd like to do is learn some unknown target function. I'll always write f for that. It belongs to this class C, but we don't know what it is. Okay, that's sort of the whole challenge. What does it mean to learn? It means we're going to come up with a hypothesis function, which hopefully is close to this target function f in some sense. Okay, so I'll get into more detail on exactly what this means in the coming slides, but first let me give you some examples of the types of classes of functions we might think about. Again, from a CS theory background, logically defined formulas where we're sort of interested in how does the complexity of learning scale with the complexity of the functions being learned. That's sort of our central concern. So we'll be thinking about classes sort of like this. Starting small, we might think about the class of all possible conjunctions of literals over n Boolean variables. So a conjunction is just a simple and. Right, here's an example of a conjunction, and this class of all conjunctions over n variables has 3 to the n elements, right? Because for each of the n variables, it might be absent from the conjunction, it might be present unnegated, or it might be present in a negated form. So 3 possibilities for each of the n variables. Right, so first thing to notice is even for the simplest learning problems we might think about, there are exponentially many possible functions in the class. So we have a non-trivial problem to try to do learning here. Okay, another class which is very widely studied, and it's kind of a workhorse in this area, is the class of all linear threshold functions. These have many names: linear separators, perceptrons of order 1, half spaces. People call them lots of different things, but here it just corresponds to you take the sign of a linear form. You look at where your point is in Euclidean space, and if it's on this side of the hyperplane, it's a positive example. If it's on this side of the hyperplane, it's a negative example. Okay, so we'll come back to these more later. Some other classes of functions that people think about, again, these have strong motivation maybe from a complexity theoretic perspective. One example would be the class of all decision trees over Boolean variables. Right? So a decision tree like this, we read a variable, the variable at the root. We always go left if we see a 0, and right if we see a 1, or left if we see false, right if we see true. And then just reading the input coordinate by coordinate, we make our way down to some leaf bit, which gives us the label. Okay, so we might want to have a system which can efficiently learn an unknown decision tree like this, right? Assuming the decision tree isn't too large. If we have n variables, maybe we want to learn polynomial-sized decision trees with an efficient algorithm. A richer class is the class of DNF formulas. These are just ORs of logical ands. And the list goes on. You can imagine really all kinds of classes of Boolean circuits, maybe with even richer structure than an OR of ands, functions of linear threshold functions, et cetera, et cetera. So kind of one of the big names of the game in this area, again, is as you go from simpler kinds of classes, things like this and this, to more complicated kinds of classes, where is sort of the boundary between tractability and intractability for learning? Right? At what point are we no longer able to learn these functions, and can we push it as far as we can? Okay, so I'd better actually tell you what the learning model is. Basically, we should think of a learning model as just kind of specifying the rules of the game. How does the learning algorithm get the data? What kind of access to the data does it have? And what is it supposed to do? What is it supposed to accomplish with its hypothesis? So people have studied a wide array of different learning models over the years. I kind of don't want you to read the fine print here. It's just to get across that impression that there are many different ways you can define a learning model. We're going to stick to, at least originally, this first probably approximately correct model, and later on, as I said, we'll augment it by thinking about what happens if we have noise, what happens if we have missing data. Okay? Okay, so let me actually tell you what the basic model is. Again, it's the so-called probably approximately correct model. It's sometimes called distribution independent learning because, as we'll see, it's a framework where the learning algorithm is supposed to succeed independent of what the distribution is. Okay, it should always be able to handle any distribution over examples. So how does it work? Like I said, we think of a learning problem as being defined by a class of functions. Okay, so this class of functions, this bold C, is fixed, and the learner knows what it is. The learner knows, hey, I'm trying to learn a conjunction. I'm trying to learn, a polynomial-sized decision tree. Okay? However, the target function, as we said, is not known to the learner. It belongs to the class, so we get to assume, yeah, I'm trying to learn, it's actually some conjunction, the thing I'm trying to learn, but of course you don't know what conjunction it is. Okay? There's an unknown and completely arbitrary distribution over the domain. This is meant to model the idea that, the world is what it is, and we don't really maybe have that much knowledge or that much control over what the world is, but we should try to deal with it anyway. So there's an unknown distribution over the domain. What does the learner get? The learner gets a sample of IID draws from this distribution. So it gets a bunch of XY pairs where each X is drawn independently from the distribution, and each Y is just f of X, labeled according to the unknown target function. The learner does some computation, cooks up a hypothesis, and spits it out. And what does it mean to succeed? It means the learning algorithm should have come up with a hypothesis which, with high confidence, with small failure probability, with probability 1 minus delta, is highly accurate. So that means that the probability over a fresh random example drawn from the distribution, the probability that the hypothesis agrees with the correct label is at least 1 minus epsilon. Okay, so it's sort of this natural epsilon delta criterion. Again, our hypothesis should probably, with probability 1 minus delta, be approximately correct, right? Have probability 1 minus epsilon of giving us the right label. Okay, so we can give a formal definition here if you want to read through it. We're interested in learning a class of function C and some time-bound t. That means that no matter what the target function is, no matter what the distribution is, if you come to me with epsilon and delta, the accuracy and confidence you'd like to achieve, my algorithm should run for at most t time steps. T might depend on epsilon and delta, of course. And with probability 1 minus delta, I should get an epsilon accurate hypothesis out. Okay? So I think it's a pretty natural model. You can see that it really sort of faithfully captures the intuition, I think, behind training and testing in machine learning. If you train your classifier on a certain type of data, a reasonable way to see how well your learning system has worked is to evaluate it on similar data points that came from the same sort of process as you train the original thing on. And again, we'll be sort of centrally concerned with computational efficiency, with the running time of learning algorithms. Very well-known results, which are covered in the first few weeks of probably any learning theory or machine learning course, tell us that if you're only worried about sample complexity, if you only want to know, hey, how many examples do I need in order to learn in this sense, the answer to that question is really generally pretty easy. For every class I'll be talking about, you can learn with a polynomial number of samples. You can learn efficiently in terms of the number of examples you need. But the running time, the computational complexity of learning is a whole different story, right? Sometimes we have efficient algorithms, sometimes we don't have efficient algorithms. So it's all going to be about running time for us. Question, yeah?
What distribution is the 1 minus delta probability measured over?
Good question. So that probability is taken over the draw of the random examples that were the data set, the training set for the learner. I don't think I said this, but I should have. So the reason we need that sort of 1 minus delta failure probability is because it could be the case that when you were getting your training set, you were just unlucky. You got sort of very atypical examples, which really didn't faithfully show you what the underlying distribution is like. So that probability is over, you could say like d to the m, like the product distribution of, if you have m sample points, it's over that space. It's over the draw of the samples. Does that answer?
Sure, yeah.
Okay.
I seem to recall seeing a variant that may have wrongly been labeled pack, where the epsilon is used as the approximation of h to f, so h minus f.
So this is the same thing we're doing here. Here these are Boolean valued functions, and so this is like the error rate. This is the accuracy, the probability that they agree on a random draw. Yeah.
Not necessarily over a point.
So since we're in a setting where these are just bits, h and x, I think it's equivalent. If you're in a regression type setting and there are regression variants, right, then you can look at something more sophisticated. Okay. So let me quickly survey for you something of what we know the state of the art for efficient learning algorithms in this framework. Unfortunately, this is only going to amount to one slide because we don't know all that much. So when the model was originally defined, Valiant showed that certain restricted classes of DNF formulas, ors of ands, or CNF formulas, ands of ors, can be learned efficiently, right? If your bottom fan-in gates are constant arity k for some constant, then you have polynomial time algorithms that run in time essentially n to the k. And it's a simple algorithm, sometimes referred to as elimination. Not too long after that, Rivest gave a simple polynomial time algorithm for learning decision lists, right? These are sort of nested if-then-else rules. If the first variable, if the first condition is satisfied, you output 1. Otherwise, you go on and check the second condition. If that's satisfied, you output 0, so on and so forth. So there's a simple greedy algorithm which runs in polynomial time to learn this. As I kind of suggested earlier, linear threshold functions, this is a very important class in learning theory. These can be learned in polynomial time via polynomial time linear programming. And also a generalization to not just linear threshold functions, where we have a linear decision surface, but polynomial threshold functions. This is my attempt to draw something like a degree 3 or degree 4 curve. If you have a degree d polynomial threshold function as the underlying function, then you can learn in time n to the d, really just by using the linear programming type approach, but over n to the d variables or metavariables. So this is really kind of one of the main tools in pack learning theory. We'll come back to it again later. And a handful of other pack learning results are known for different classes. You can learn like parity functions using essentially Gaussian elimination. You can learn some extremely restricted types of branching programs. These are branching programs of width at most 2 with other constraints on them. Some geometric function classes. Unfortunately, this is about it. Not much more than what's up on this slide or constitute the entire collection of function classes that people have been interested in and have been able to show pack learnable in the original model. So that's kind of tough, right? Learning is not so easy in this framework. Given this challenge, people have said, okay, maybe I'll relax my standards a little bit. Someone talked earlier in this workshop about redefining the problem when we have trouble solving the problem, right? So maybe we'll be interested still in more than polynomial time algorithms, but algorithms which are faster than some kind of brute force search, running in time significantly better than 2 to the n. So quasi-polynomial time would be maybe n to the log n. Sub-exponential time is maybe 2 to the square root n, something like that. And a handful of results are known here. It's known that you can learn decision trees in quasi-polynomial time. You can learn DNF formulas in sub-exponential time. You can learn various kind of restricted classes where you combine a few half spaces. If your half spaces have small integer coordinates, you can do something like this. And for all these results, I don't want to get into any details on this, but linear programming over an expanded feature space is really the key technique that underlies each of these results. Most of the work is to prove some kind of structural result saying, hey, my intersection of half spaces has a low degree polynomial threshold function representation, right? So you sort of think like a complexity theorist, prove something about the structure of the functions, and then we just use the same old algorithm to learn polynomial threshold functions. This really is the state of the art. Okay, unfortunately, not only is there not that much good news, but there's some very strong bad news in this framework too. Okay, we have a range of negative results from cryptography and from other areas telling us about limitations on pack learning, that we shouldn't expect to learn certain classes in small amounts of time. So I don't really want to go through all these things individually in a lot of detail because I want to get to the noisy and missing data part of the talk, but the existence of public key cryptography, where the decryption function, under various number theoretic assumptions, is believed to be not so hard to compute, tells us that we shouldn't expect to learn, for example, polynomial-sized Boolean formulas. Even more restricted classes, if you look at specific constructions of pseudorandom functions, which are believed to be secure in the literature, tell us we shouldn't expect to learn weaker classes, and even a class of fairly simple depth 2 circuits, intersections of linear threshold functions. Regev came up with a crypto system about 10 years ago, which nobody's cracked yet. And if you believe that that crypto system is indeed secure, you won't even be able to learn this class efficiently. Yuval, yeah?
One question about the quantifier of this here. So
Yeah.
the negative results are about a specific distribution.
Negative results. So if I just say this class is not pack learnable, what does it mean? It means there is no algorithm which works for all distributions. However, for each of these cases, you can actually if you look at what's really going on, you have hardness, at least for the first two, I'm not sure about the third one, you actually have hardness even against just the uniform distribution, even against very simple distributions. Yeah. So more recently, there's been other exciting work. Yeah.
I think there's something I could
Sure,
just
yeah.
repeat once more. So n is the dimension of the vectors you're getting.
Exactly. So each example is like
S, the training set. Are the results? Do people do? Are these asymptotic in size of the training set, or it can't work with a training set of size 1. So
No, so these results say, pick your favorite polynomial bound on the size of the training set, n squared, n to the 5th, n to the 100. These results tell you there's no algorithm which can learn, say, this class of functions if you give it a training set of size n to the 100 or whatever polynomial size training set you want to give it.
So are those poly there's referring to the size of the training set or the time it takes to run the algorithm?
So these, sorry, yeah. When you see poly here, think of it as some fixed polynomial, n squared, right? Or yeah. So there's no. Let me maybe rephrase this bullet a little bit more precisely. It says that there is no algorithm which runs in polynomial time. You can give it a polynomial size training set. So for n squared, n to the 5th, n to the 10th, n to the 100, there's no algorithm which takes a training set of that size, runs in that much time, okay, and learns here, you could say, the class of depth 5 circuits of linear threshold function gates of size n squared.
But you might have something which takes poly of n training samples and runs an exponential time.
Yeah, for every class that I'm talking about in this entire talk, there's always a learning algorithm which takes a polynomial size training set and runs an exponential time. Yeah, the sample complexity, the information theoretic question, is not a very difficult one. It's all about the computational complexity for this work, yeah. Yeah, good question. Okay, so I'll be very brief on this slide because I want to get to the other stuff. There are more recent sort of average case hardness assumptions, an assumption having to do with the time complexity of refuting random CNF formulas. And Daniele and Shalev-Schwartz have shown that if you're willing to make the assumption that we don't have fast refutation algorithms for these random CNF formulas, then some really simple classes seem like they are indeed going to be hard to learn. We're not going to be able to learn DNF even with a mildly super constant number of terms. We're not going to be able to learn intersections of even just a little bit more than log n many half spaces, and so on. So this is strong bad news, right? This talk has been a real downer so far. All I've been doing is telling you, this is probably not learnable. We don't know how to learn that, so on and so forth. Pack learning looks pretty tough. And to make things worse, I haven't even mentioned noise yet, right? Hopefully we're going to do something about learning in the presence of noise, learning with missing data. That's only going to make things harder, right? So how are we possibly going to cope with this situation? Well, we're going to do the classic theorist's dodge of changing the goalposts, trying to solve some different or in some sense easier problem. But before I get to the part about making it easier, let me tell you a little bit about what I mean by noise for the rest of this talk. So there are some noise models which are so challenging and annoying that it would just depress me and depress you for me to talk about them. I'm not going to talk about those. Instead, I want to mention this, I think, still quite interesting noise model known as agnostic learning, which is about 20 years old now. So the way we'll model noise is we're going to say, I no longer am assuming that the function I'm trying to learn necessarily belongs to this particular class C. The function now can be arbitrary. And you can think of the deviations of this function f, right, from the functions in the class as being like the noise, the sense in which it no longer is faithfully like in this nice clean scenario. So there's this very natural notion then, this parameter opt. Opt is defined relative to your class C and your distribution D. What is it? It's sort of the minimum distance of any function in the class to the target function, to the function f, right? So if your function f is actually in the class, opt is 0, right? Because you're actually in the class, there's no distance. But maybe, if your class is the class of all linear threshold functions, maybe the best linear threshold function is such that it only agrees with the target function 90% of the time. In a setting like that, opt would be 0.1, okay? So the agnostic learning model says, hey, I'm not assuming my function f belongs to the class. It could be arbitrary. But I'm also saying, I don't have to learn the function to super high accuracy. Instead, I just want to construct a hypothesis whose error rate is at most opt plus epsilon. Or, sometimes that's going to be rough. Maybe we'll still be interested if we can achieve, 3 times opt plus epsilon, 10 opt plus epsilon, or even something like square root opt plus epsilon. Okay? So we call it agnostic learning if we can really get opt plus epsilon, which corresponds to having our hypothesis predict the value of the function really almost as well, with an epsilon accuracy as well as the best function in the class. And if we can get something like 5 opt plus epsilon, square root opt plus epsilon, we call that quasi-agnostic learning. Okay? So not as good, but still good for something. So it won't be a surprise. We said earlier, pack learning is hard. If you introduce noise, go to this agnostic model, things only get harder. Even simple classes, which we could learn in the original pack framework, like linear threshold functions or half spaces, even conjunctions, we cannot learn in the agnostic model. Okay? So what are we going to do? Well, we're going to change the goalposts, like I said. right? What I've been talking about so far, this pack learning model, we have that the distribution D is unknown. It's an arbitrary distribution. And that really means, for the purposes of analysis, it's adversarial. We have to deal with the worst possible distribution that anyone might have cooked up. Right? We're going to relax this. We're going to change the game and say, you know, I'm going to assume that the distribution is something that I know what it is. And in fact, I'm going to assume that the distribution is nice in some sense. So kind of the standard assumptions that are the subject of a lot of work here are that if we're dealing with, say, binary data, where our data points, our examples are n-bit strings, then the standard assumption is that the distribution maybe is just the uniform distribution over n-bit strings. Or maybe it's a product distribution where we have independence among coordinates. If the domain is Rn, if we have vectors of real numbers as our sort of labeled as our examples, then we'll typically assume that the distribution is just a standard Gaussian distribution, or maybe a non-standard Gaussian distribution. But so the name of the game is that we're relaxing the assumption on noise. We're in this agnostic setting now, but we assume more about the data in the sense of the distribution. So we sort of let go of some control or some assumed control over the labels, and we assume more about the examples themselves. Okay? So what happens in this setting? What can we say? It turns out there are a bunch of things that can be said here. First, I'll sort of survey briefly some actual agnostic learning results where we can really achieve opt plus epsilon as good as you could hope to do. So in work about 10 years ago, it was shown that one can learn linear threshold functions in something like polynomial time here. If you're willing to think of the epsilon parameter as a constant, then this is n to the 1 over epsilon squared. It's a high order polynomial, but it is some kind of polynomial time. And the technique that was introduced in this work really is at the heart of all of the agnostic results I'll tell you about. It's a kind of L1 polynomial regression algorithm which reduces the agnostic learning problem to the problem of designing low-degree polynomial approximators. So all of the later agnostic learning results I'll tell you about were really achieved by using this technique and doing complexity theoretic work of showing, hey, these functions that I'm interested in, I can approximate them in a suitable sense by low-degree polynomials. So one example of such work is work on learning intersections of several half spaces. Right? We have only a relatively mild dependence on the number of half spaces. It's logarithmic, although it is in the exponent. And these Gaussian surface area bounds are sort of what underlies the existence of these low-degree polynomial approximators. Similar results have been achieved for learning low-degree polynomial threshold functions. So when we have these degree D surfaces, you can similarly do something, again, by proving Gaussian surface area bounds. But it's not all roses, right? We do have some limitations on what we know we can achieve here. In particular, it's been shown that we should not expect to have really polynomial time algorithms, polynomial in n and 1 over epsilon. Right? This lower bound was given, which shows that even for this sort of very clean and simple problem, learning one linear separator under the Gaussian distribution, you're not going to be able to get opt plus epsilon under some assumption about the hardness of learning sparse noisy parity functions. Okay? So there's a lot of room, though, between this n to the 1 over epsilon squared and this n to the log 1 over epsilon. It would be very interesting to understand more precisely what is the real complexity there. So this is all under the Gaussian distribution, which in some sense I think is really the easiest non-trivial distribution for learning. You have this radial symmetry, really is just about as nice as things can be. If we are willing to lower our standards and think about just quasi-agnostic learning, it turns out that you can sometimes do significantly faster. So in the same early work, it was shown that you can achieve something just not that much worse than opt. Opt times square root log 1 over opt. So not that much, this additional factor, this square root log 1 over opt. We wish it were 1, but it's probably not that tremendous a number. And this is truly polynomial time. In fact, the algorithm here runs in linear time in the length of the data. You just read it, and I don't want to use the word real time after everything we've seen this week, but it's really a very simple linear time algorithm. This was improved at the expense of some more running time, so you can learn to accuracy 5 opt plus epsilon or 10 opt plus epsilon in polynomial time. And quite recently, it was shown how you can really get like a polynomial time approximation scheme. You want 1.01 times opt plus epsilon. You can achieve it, but you're going to sort of pay for it in the exponent. So this result really kind of interpolates between the results we saw before and the simplest and fastest result on top. Okay. So I don't want to go into great detail on these results. These are results for agnostic and quasi-agnostic learning under the uniform distribution on the cube. The cube is harder than the sphere. You have less symmetry. Things aren't quite as nice. Your half spaces can sort of lie arbitrarily close to some points, which is sort of obnoxious. But by dint of complexity theoretic work, people have been able to sort of almost match the kinds of results we saw for the Gaussian distribution in the setting of the cube. And there's really only one result I know of on quasi-agnostic learning, learning to accuracy worse than opt plus epsilon in the setting of the cube. This is work which achieves this really rather ugly, I'm afraid, dependence. Again, we'd like to have opt here. What we have here is worse than square root of opt. It's worse than opt to the 0.1, but it's some kind of dependence. At least it depends only on opt, right? If we had a dependence on n or something, the dimension of the problem, then we wouldn't really think of that as agnostic or quasi-agnostic learning anymore. But this is at least a fairly fast algorithm. It's not quite polynomial in epsilon, but it's really linear in the number of bits you have to read. Information theoretically, you need n-bit strings, and the running time I'm showing you here is bit complexity. So it's linear in terms of sort of the bit complexity, but unfortunately you need quasi-polynomial amount of data in terms of the dependence on epsilon. And actually the algorithm for this comes from learning from incomplete information, the next topic which I promised you, which I want to turn to at this point. So we've talked so far entirely about settings where we're learning from these n-dimensional vectors, that's our example, and then we have a binary label. And we've always been assuming that you get the entire n-dimensional vector as your example. Each data point, you can see every coordinate, right? But in fact, that's sometimes an extremely unrealistic assumption. The truth of the matter might be much closer to the opposite, that in a typical data point you get, you really can see almost none of the n coordinates, as opposed to being able to see all of them. Think about like a medical scenario or something. Maybe you have a different feature for every possible diagnostic test you might run on the patient, or every possible treatment you might run on the patient. You're not going to subject the patient, to 100 different treatments. You're probably not going to run 100 different diagnostic tests on the patient. You might run 2 or 3 tests. You might give them 1 treatment or 2 treatments, and then you see how they respond. So your labeled data point will only have 1 or 2 coordinates out of all the sort of possible coordinates, right? So it's very much not like this idealized setting we've been talking about. But it's interesting, of course, to study. Can we say something, can we give some theoretical guarantee on learning in a setting like this, where we have very little available data within each data point? So this has indeed been studied. It's sometimes referred to as this restricted focus of attention, or RFA learning model. I'll explain it to you in this slide. As before, we're trying to learn an unknown function f from this class C of known functions. As before, we have a distribution over possible examples. But what really changes is that now, if it's the so-called 1 RFA model, which is the most intensively studied model, the learner doesn't see all n coordinates of any given data point. Instead, the learner only sees 1 coordinate of the data point. Okay, so in the usual scenario, we would get to see the entire n-bit string and then the label. In this 1 RFA learning scenario, you get to see 1 of the n coordinates as well as the label. So much, much less information is available to the learning algorithm. Okay? But we want to do the same thing we were trying to do earlier, come up with a high accuracy hypothesis H with high confidence. Okay? So kind of a cartoon of how learning proceeds in this model. We have the learner and we have the source of data. The learner says, I'd like an example, and please make it an X7 example. Show me the 7th bit. So it gets back something like this. The learner says, yeah, I really could stand to learn more about what's going on here, about the 7th coordinate. Please show me another X7 example. And it gets back something like this now. Maybe this time the 7th coordinate is 0, the label is 1. So on and so forth, and at the end of the day, the learner has to spit out some high accuracy hypothesis based on this kind of interaction. So what can we say? Well, we can say some bad news, of course, right? It's very easy to see that if your distribution is unknown and arbitrary, it's almost impossible to do anything in this framework, right?
So just to understand the
yeah.
In pack learning, the learner can't specify anything about the examples
Yeah.
you want to see. And here, you're allowing the learner to specify something about it.
Yeah, so strictly speaking, the way I've presented it, the learner does get to do the specification. Probably the first thing one always does in studying this model is say, what does the learner really have? It just has statistical information about the correlation between this coordinate and the label, right? And it has that kind of information for each of the n coordinates. So that's another way of specifying the model. Yeah.
So basically, the examples are being drawn from the overall underlying distribution and it's being projected onto this.
Exactly. You get to see the one-dimensional marginal of the n-dimensional distribution.
About this kind of access already in sort of the pack setting.
So that's exactly what this does, right? This is just like the pack setting, but where you only have this kind of access.
But I'm asking, you could also allow the learner to influence the X on which it gets an answer.
Do you mean like, I'm not quite sure what you mean. So here you get to...
I mean, when the learner presents an X and gets the
The learner is given an X. The learner doesn't actively select an X. Yeah.
What happens when you change the model and you allow the learner to choose which X?
Yeah, good. So that's pack learning with membership queries is the buzzword. There's a whole other talk with a different set of results.
Okay.
Some things become significantly easier. Some things don't become so much easier. Some of the hardness results still hold. Some of them don't still hold. Okay. So it's just a different ball game. Yeah, okay. Yeah. But in practice, my impression is people will sometimes say, it's really not so easy to have that kind of access, right? So people have done experiments where they try to run these like membership query learning algorithms on, say, recognizing handwritten data, and the algorithm starts very quickly asking for these bizarre pseudo digits, which look like some kind of, is this a 2 or is this a 3? And like we don't know how to label it then. So yeah, this kind of thing I think is maybe it's a little bit more difficult to put that in the context of real systems, but okay. Good. So this is a hard model if the distribution can be arbitrary. Basically, how are you going to tell this function in this distribution from this other function in this other distribution? You just don't have access to enough information from these very restricted views to be able to tell things apart. Even if your distribution is as nice as it gets, even if your distribution is uniform over n-bit strings, it's information theoretically impossible. It's easy to see this, to learn sort of functions where you have non-trivial associations. I don't want to define this precisely, but maybe the example makes it clear. Suppose your unknown target is the parity of two variables. So it's some xi, xor, xj. That's the target function, but you don't know what variables I and j are. It's easy to see that in this framework, it's completely impossible to learn, right? Because you only ever get to see one bit of any example. So you're just never going to see any correlation between any bit and the label. There's no chance of learning here. So can we do anything? Well, it turns out we can do something for the right function classes. So it comes back again to these linear threshold functions. The class we'll think about again is all n-variable linear threshold functions. We'll think about this nice distribution, uniform over the cube. So this is a paper from, I think, either the very first or the second Fox conference. Chow showed that if you get 2 to the n examples like this, again, the example is always just this bit and this bit in the label, this bit in the label, right? But if you have access to, this gives you such good statistical information that you really know exactly the value of the correlation under the uniform distribution between each coordinate and the label. Another way of putting it is that you know the exact values of the degree 1 Fourier coefficients of the function. If you know that, that is enough information theoretically to learn to perfect accuracy. So another phrasing of this Chow result is that the degree 0 and degree 1 Fourier coefficients of a linear threshold function uniquely specify it actually among the space of all Boolean functions. Okay? And there's some very cute proofs of this in sort of modern language. Of course, we want to do something faster than 2 to the n time, and we want to, we're willing to give up some accuracy. Is there a robust version of this theorem? So it turns out there is a robust version of this theorem. If you want to learn to say just some small constant accuracy, then something like polynomial in n and 2 to the 1 over epsilon squared examples suffices for that. And people worked more on this and were able to actually come up with algorithms which could do quite well for this problem. So again, this is the algorithm I referred to earlier. It runs in linear time in the bit length of the entire data set that it has to use. And it's not quite polynomial in terms of the accuracy parameter, but it's fairly close. And there's some hope still of maybe being able to improve it. So this is something which we do know how to do in the 1RFA model. I think it would be very interesting, and as far as I can tell, it's completely unexplored, to go beyond 1, right? So okay, you get to see 1 bit of the data. That's really about as pessimistic as it gets, right? What if I show you 2 bits? What if I'm willing to show you, I don't know, log 1 over epsilon bits or 1 over epsilon bits or something? I think there's, this is really one point on the curve. You see the minimal possible amount of data. We understand what happens if you get to see all n bits, but there's a lot of space in the middle, and I think there may be an opportunity for some interesting results sort of to trace that curve if we can understand more of what's going on. Okay, it looks like I'm just about, well, I'm not quite out of time. I have maybe 2 or 3 minutes left, but do you guys want to see something quickly about unsupervised learning?
Sure.
Okay. So this is a framework. It's sort of cooked up by design to be similar in spirit to this pack learning model, except that there are no functions. There are no labels anymore. Okay? We're going to be in a setting where we just want to somehow extract some meaningful information from a scenario where we just don't have access to any kinds of labels about the data at all. So this is a model that was introduced at least into theoretical computer science about 20 years ago by Renit and some colleagues. Things like this have been studied in statistics really for decades, though, under the name of density estimation. It really is just like pack learning. Like if you were to guess what the model should be, and you just said pack learning but with no functions, you would come up with the right model. So how does it work? Learning problems now are going to be defined by a class of possible target distributions for us. Okay, so no functions, just the unknown distribution plays the role of the unknown function. Okay, so the target distribution belongs to this class, but we don't know what it is. We know that it belongs to this class. We know the class, but we don't know which guy it is from the class. The learner gets an IID sample of draws from the distribution. Again, no functions, so it's just X. The learner does some computation, spits out a hypothesis distribution, and we want, with high confidence, right, with small failure probability, the hypothesis distribution to be close to the target distribution. And people mostly study this with this fairly stringent total variation distance measure, or L1 distance between the two distributions. Okay, so this slide just has two toy examples of results on learning distributions. So here's a one-dimensional example. You could think about learning this class C of all k-modal distributions over a universe of n elements. Okay, so k-modal means k peaks and valleys if you were to draw sort of the plot of the probability density function. Okay, and we have quite efficient algorithms for learning this class. These algorithms actually run in close to linear time. I'm hiding some log factors here, so this slide is not 100% honest, but the algorithms run in close to linear time in the sample complexity, and the sample complexity is known to be optimal. So in one dimension, sometimes we can get these very strong results where we know the exact information theoretic correct sample complexity, and we also are able to come up with algorithms which run in really the right amount of time as well. In high dimensions, things get a lot harder. So this is a cartoon picture of a mixture of three one-dimensional Gaussians. I'm not enough of an artist to draw a mixture of n-dimensional Gaussians, but in very impressive work, it has been shown how to learn mixtures of, say, k Gaussians over n dimensions. And these are arbitrary Gaussians. They don't have to be axis aligned or anything in polynomial time, at least as long as the number k is constant. Okay? So these are examples of sort of basic results, analogous to what I was saying about conjunctions and linear threshold functions and decision lists and so on, for the distribution learning problem. We don't have a notion of noise. We don't have a notion of missing data. But of course, we want those notions, right? So how do we sort of cook noise into the picture? Well, we can have this notion of agnostically learning distributions, which again is defined entirely analogously to agnostically learning classification rules or Boolean functions. The distribution is now assumed to be arbitrary. Right? We have this notion of opt being the minimum distance from the arbitrary target to a distribution in our class. And we'd like to come up with a hypothesis distribution H. Whoops, sorry, this should be an H instead of a D prime. We want a hypothesis distribution whose error is at most opt plus epsilon, or maybe 5 opt plus epsilon, or so on and so forth. So the same kind of notion of doing as well as the best distribution in our class. And I'll close by just telling you about two results on agnostic or quasi-agnostic learning of probability distributions. So this is a one-dimensional problem. Okay, we're going to consider this class of T piecewise degree D polynomial distributions. So they're distributions over some segment of the real line. And here T would be 4, D would be 3. Right? This is some wacky distribution where within each of these 4 pieces, the probability mass function is a degree D, a degree 3 polynomial. Okay? So it's known how to agnostically learn this class of distributions, or I should really say quasi-agnostically. It's 3 opt plus epsilon is what's achieved. And the latest result, done with some impressive algorithmic machinery, runs in, again, essentially linear time in the number of samples. So the number of samples is this. The running time is essentially this. I'm hiding a log factor again. And this is also an information theoretic lower bound. You need this many examples, no matter how slowly your algorithm is allowed to run. Okay? And this turns out to be useful because if you can achieve this kind of agnostic or quasi-agnostic learning, you can use this as sort of a subroutine to get learning results for many different classes of distributions that people have studied. You prove a structural result saying, hey, you're interested in log concave distributions. Actually, they can be well approximated by distributions like this. And then the sort of quasi-agnostic guarantee tells you that the approximation is enough. You can successfully learn the distribution which is being approximated. Okay? So kind of a one-dimensional example, and I'll make this my last slide. Very recent work that'll be in the upcoming Fox conference. The first work really on high-dimensional, almost agnostic, quasi-agnostic distribution learning. So the classes of distributions that are being learned here, they're over n dimensions. They may not look that complicated or that impressive, right? You're trying to learn a single n-dimensional Gaussian, or you're trying to learn a single n-dimensional product distribution over the cube. Neither of these are hard learning problems if you have no noise. If you have no noise, for the Gaussian, I'll just learn the covariance matrix by sampling. I'll learn the mean by sampling, and I'll spit out those parameters, and I'll have a high accuracy hypothesis. For the product distribution, if you have no noise, I'll just estimate the probability that the first coordinate is 1, the second coordinate is 1, so on and so forth. These are easy learning problems if there's no noise. If you're in high dimension and there is noise, it's very, very non-trivial to learn these classes. It's easy to learn these classes if you're willing to have something like n times opt as your error rate, or square root n times opt as your error rate. If you want to get an error rate which is completely independent of the dimension, that's much more difficult to do. It was only achieved very recently in this upcoming paper. And you can see that, at least for, say, learning a single Gaussian, it's really very good, right? They only have a small kind of additional factor above opt plus epsilon, which is sort of the ideal thing you would want. And the result is a little harder for product distributions. Okay? So we're really at the point now where the community is just starting to make progress on these agnostic or quasi-agnostic high-dimensional distribution learning problems. And my guess is there's going to be a lot of future work along these lines. I had one slide on learning distributions from partial information, but since I'm a little bit over time, maybe I'll just cut to the conclusion. The summary is that we've talked about a range of different models and results for learning from noisy and incomplete data. There are a lot of interesting algorithmic challenges, and I should have given this apology at the beginning of the talk. I'll give it now at the end of the talk, which is really very little is known, and it's not because I'm hiding it from you, just the community doesn't really understand very much about what can be done, say, in a streaming setting, in a real-time setting. Even achieving linear time, as we saw, is quite a challenge for most of these problems. We often have polynomial time, or even something which you have to be sort of in a good mood to call polynomial time for a lot of these problems. So I think there's a lot of work to be done in terms of trying to get stronger results, which would maybe adhere more closely to the kinds of settings that we in this room are interested in. OK, thanks. Yeah.
So in the agnostic setting, is there anything that can be, is there any relation to coding theory? I mean, that if you think of the concept classes consisting of code words or something like that, so any example you see cannot be too close to two of them or something. Is there any kind of connection of that kind?
That's an interesting point of view on it. Nothing comes to mind. Yeah, I don't know of anything. If I wake up in the middle of the night and realize, oh yeah, that's thus and such, I'll send you an email. But off the top of my head, I'm not coming up with any connections. Yeah.
What's the connection of the image to the
Oh, it's just, yeah, I guess maybe implicitly you guys are the cow or something. I'm not really sure. This is a Mark Tanzi painting. They used to have it in the Met. I've been fond of it for a while. Yeah. It's called the Innocent Eye Test. So, yeah.
whether a cow can recognize a cow?
Yeah. And I think that's a Monet haystack in the background. But
Yeah, thank you very much.
Can I ask a really high-level question? I understand